Hey future seekers, tonight we begin with a question that is as mysterious as it is captivating. Did we, in some subtle way, summon 3I/TLAS? Perhaps the universe itself is listening, and our human activities have a ripple effect that reaches far beyond our imagination. Tonight we explore the serene, speculative and science-backed possibilities of this interstellar visitor, gently unravelling what its presence could mean for our future. Before we settle in and begin our peaceful journey into the future, take a moment to like this video and subscribe, only if what I share here truly resonates with you. Your support helps me create more of these stories, and if you feel like it, let me know where you're tuning in from and what time it is. It's always fascinating to see the many corners of the world where we connect. Now, dim the lights, make yourself comfortable, and let's ease into tonight's journey together as we explore what lies ahead. Chapter 1. The Calm Arrival, Understanding 3I/TLAS. Imagine for a moment drifting in the quiet expanse of space. Stars twinkle in patterns older than humanity itself. Somewhere far from Earth, a slender object glides through this vast darkness, a visitor from a distant star system. Astronomers call it 3/ATLAS, a mysterious interstellar object that passed through our solar system. Its shape is elongated, perhaps tumbling slowly, reflecting the sunlight in ways that make it shimmer like a cosmic lantern. This is not just a story of a celestial body passing by. It is a story that invites us to reflect on our place in the universe. What is the likelihood of a lone object from another star system finding its way here? And more intriguingly, could our collective human activity, our powerful radio waves, our electromagnetic footprints, even our explorations into space, have, in some subtle way, drawn this object closer? Scientists speculate that interstellar objects are rare, yet they may be more common than we first imagined. Every star in our galaxy is surrounded by a cloud of objects, some drifting into the cold void of space. Some might wander close to planets like Earth, barely noticed, quietly whispering their secrets to those who watch and listen. Consider the story of Oumuamua, the mysterious object detected in 2017. Its strange, elongated form sparked debates about its nature. Was it a natural fragment of an alien planet, or something more enigmatic? 3I/ATLAS shares similar traits, and its arrival challenges us to think deeply about the subtle ways humanity interacts with the cosmos. It is soothing to imagine these silent travellers moving gracefully through the solar system, their paths governed by gravity and momentum, unaffected by our day-to-day concerns. Yet the question lingers quietly in the back of our minds. Could our presence, our light, and even our sound in the universe be like a faint beacon, a soft signal, calling distant objects toward us? As you breathe slowly, letting each inhale and exhale relax your body, picture 3I/ATLAS moving past planets, asteroids and comets. Feel the calm of this cosmic journey. The universe is vast, ancient and patient. It doesn't rush, and neither do we. Tonight, we are simply observers, witnessing a quiet dance between our world and the deep, dark reaches of interstellar space. Scientists are beginning to map the likely paths of such objects, using delicate calculations and simulations. Each observation reveals more about their trajectories, their composition, and perhaps about ourselves. Our curiosity, our observations, and our presence in the cosmos may be more interconnected than we realize. As Chapter 1 draws to a close, allow your mind to float gently with the idea of this interstellar traveller. Let it glide silently across your imagination, a reminder of the serene mysteries that surround us. Chapter 2. The Science Behind Interstellar Objects. how 3I/ATLAS could be a sign of something greater. As we continue our journey, let us take a closer look at what makes 3I/ATLAS truly extraordinary. In our solar system, we are familiar with asteroids, comets, and meteoroids, small celestial bodies bound by the sun's gravity, orbiting predictably along elliptical paths. Their origins are typically well understood: the asteroid belt between Mars and Jupiter, the Kuiper belt beyond Neptune, or distant comets forming at the edge of the solar system. 3I/ATLAS, however, does not follow these familiar patterns. Its trajectory is hyperbolic, meaning it is not bound to the sun. It is passing through our solar system only once, moving fast enough to escape again, never to return. This immediately raises questions. How common are interstellar visitors? And what can we learn from this fleeting encounter? Scientists estimate that interstellar objects might pass through our solar system more often than we realize, but most are too small, too dark, or too distant for current instruments to detect. 3I/ATLAS was fortunate to be large enough, about a few hundred meters in length, and reflective enough to catch the attention of ATLAS, a telescope designed specifically to monitor near-Earth objects. Its discovery reminds us of the delicate balance between chance and preparation, between cosmic invisibility and observation. But beyond the mathematics and physics, there is another layer of curiosity. Consider the shape of 3I/ATLAS, elongated, cigar-like, spinning slowly as it travelled. Such a shape is unusual but not impossible for natural objects, yet it sparks the imagination. Could this be an ancient fragment of another star system, a shard from a distant collision? Or could it, in some remote sense, be evidence of something more deliberate? We do not yet have answers. The tools of astronomy, while powerful, are limited by distance, light, and time. We can measure its motion, its brightness, its rotation, even estimate its composition, mostly rock and ice, but the origins of its journey, and whether there is a pattern to it, remain tantalizingly out of reach. Now, let us gently shift our focus to another fascinating idea: the possibility that our own actions, our technology, our radio signals, our probes reaching into space, could have an influence on such objects. Humanity has become a detectable presence in the cosmos. Radio and television waves have been radiating outward for over a century, travelling at the speed of light, forming a bubble of signals tens of light years wide. Our deep space missions, like Voyager and New Horizons, carry artifacts of Earth, including golden records intended to communicate our presence to distant civilizations. It is worth imagining, in a calm and deliberate way, how these signals travel. They ripple through the darkness, interacting with cosmic dust, solar winds, and magnetic fields. Perhaps somewhere, in a distant solar system, a particle, a planet, or an object sensitive enough picks up traces of these ripples. Could 3I/ATLAS be responding to a faint gravitational nudge, or a subtle resonance caused by these interactions? Even if we approach this idea purely scientifically, without assigning intention or purpose, it remains a remarkable thought, that the universe, vast and indifferent, may still respond to our existence in ways we cannot yet measure. Each interstellar visitor becomes a story, a messenger carrying the quiet secrets of distant worlds, passing through our solar system as a fleeting guest. Picture 3I/ATLAS as it glides past Mars, illuminated by sunlight, tumbling silently. Visualize the immense distances it has travelled, the countless stars it has passed, and the immense timescales involved. Its journey invites us to reflect on our own position in the cosmos. Small, curious, but increasingly visible. In the chapters ahead, we will explore how humans might inadvertently attract more interstellar visitors, the subtle signals we emit into the galaxy, and what scientists speculate about the future of such encounters. We will dive into the possibilities of intentional communication, the ethics of detection, and the profound questions that arise when we realize our civilization is not entirely hidden in the cosmic darkness. For now, allow yourself to linger in the image of 3I/ATLAS spinning gracefully through the void, a solitary traveller whispering secrets from beyond. Breathe in the calm of this cosmic dance and let your mind gently follow the motion, imagining the stillness and infinity of space. Chapter 3: The Signals We Send. How Earth Lights Up the Darkness. Close your eyes for a moment and imagine Earth at night as seen from far away. A blue-green bead studded with quiet pinpricks of light. But beyond those lights, beyond the glow of cities, Earth also emits something more subtle. Ripples of radio and microwave energy, faint beams of laser light from laboratories, and the deliberate pulses of spacecraft radio beacons. These are the signatures of a technological world, our quiet, expanding footprint in the dark. Let's gently unpack what those signals are, how they travel, and what they might mean for a passing interstellar visitor like 3I/ATLAS, or for any observing intelligence far beyond our solar system. First, the radio bubble. For over a century we've been broadcasting radio and television signals into space. Those signals travel outward at the speed of light, forming a spherical shell around the sun, an ever-growing radio bubble. Estimates vary depending on what you count as detectable transmission, but that bubble now reaches on the order of tens to perhaps a couple of hundred light-years in radius. In other words, the earliest radio waves we sent a century ago have now passed many nearby stars. This expanding bubble is our first, involuntary beacon to the galaxy. But there are two important differences to keep in mind between the kinds of signals we put into space. The first is leakage. These are the weak, omnidirectional broadcasts that spill into space as a byproduct of our daily life. TV, AM, FM radio, early radar. They spread out in every direction, and their strength falls off rapidly with distance, following the inverse square law. For a civilization even a few light years away, detecting ordinary leakage would be extremely challenging unless they had enormous, sensitive receivers and were listening carefully in the right frequency bands for a very long time. The second kind is intentional, high-power, beamed transmissions. The Arecibo message of 1974 is a classic example. A purposeful, tightly focused broadcast sent toward the globular cluster M13. It used a powerful transmitter and the dish's focused gain to send a narrow beam of information, a short symbolic greeting of humanity, that will take tens of thousands of years to reach its target. Beam transmissions like that carry far more energy in a given direction and can be detectable much farther away along that narrow path. The Arecibo broadcast was more of a demonstration of capability than a practical attempt at contact, but it shows how different beamed messages are from everyday leakage. A related and modern consideration is the idea of directed energy and power beaming. Scientists and engineers are exploring the use of high-power lasers and microwaves for things like spacecraft propulsion, asteroid deflection, and long-distance communication. These systems concentrate enormous amounts of energy into narrow beams. Researchers have pointed out that such beamed energy, even when used for mundane engineering purposes, would be highly detectable across interstellar distances if you happened to be in the beam's path or had instruments capable of seeing it. In short, our technological advances may unintentionally create bright, narrow signatures in the sky. This leads to a gentle, thoughtful question. Could a civilization, or a probe, notice those beamed signatures and respond? That's the heart of the "did we summon it" speculation. It's not a suggestion of immediate drama, but rather a chain of cause and effect to consider. If a distant observer saw evidence of concentrated energy or unusual radioactivity coming from a small planet, it could flag that system as worthy of further investigation. Perhaps they would send a long-range probe or an autonomous shepherd to investigate interstellar traffic, or more likely they would simply catalogue us as another point of scientific interest. The universe, if populated with observers, might be more curious than predatory. The scientific community spends much time weighing risks and benefits of actively transmitting messages versus listening quietly. The debate over active SETI, or MITI, messaging to extraterrestrial intelligence, highlights both the technical possibilities and the ethical complexities of intentionally announcing ourselves. There's another subtlety to the physics. Interstellar space is not a perfect vacuum. Radio waves scatter, are absorbed or dispersed by the interstellar medium, and can be smeared out by magnetic fields and charged particles. That means even powerful transmissions get blurred and weakened over the tens of light years they travel. So, detectability depends on many factors: transmitter power, beam focus, frequency, background noise at the receiver, and the patience and instrumentation of the listeners. A civilization must both look in the right direction and have sensitive enough equipment to detect the faint whisper of a distant technological world. To keep this calm and grounded, picture a distant astronomer, centuries from now. A small team in a quiet observatory notices a narrow spike in a radio band, a periodic, non-natural pattern among the background hiss. It's not violent, it's not dramatic. It's like catching the rhythm of a distant heartbeat. They tag it, study it, and note the coordinates. In their logs, our tiny planet is marked as a place with something very much worth understanding. Over the course of millennia, that recorded interest might translate into probes, or into the curious passage of interstellar objects sent to study points of technological activity. The delay is vast, and the patience required is beyond human experience, but in cosmic terms, it's merely another long observation. Another practical thread we will follow in later chapters is the idea of techno-signatures beyond radio. Engineered artifacts, atmospheric pollution, city glows, or anomalous thermal patterns could serve as another kind of beacon. In coming chapters, we will explore how non-radio signs of technology, from waste heat to engineered molecules in the atmosphere, might be easier or harder to detect than radio leakage, and what that implies about being noticed. Before we close this chapter, a brief calm story to settle the imagination. Imagine a probe the size of a pebble, launched centuries earlier by a distant civilization that once catalogued bright beamed emissions coming from our system. That pebble drifts across empty light years, an autonomous archive and scout. One day it intercepts a small icy rock on a tangent path, an object like 3I/ATLAS, and gently uses it as a carrier, hitchhiking on a natural object's trajectory to save energy. The pebble doesn't need to summon the rock, it simply takes advantage of the cosmic traffic to arrive where curiosity led it. Whether this exact scenario has happened is unknown, but it is a physically plausible mechanism that blends nature and technology in a gentle way, and it reminds us how subtle the interplay between us and the cosmos can be. Chapter 4, Technosignatures, the subtle footprints of civilization. Sit back and breathe. Picture Earth as a small lantern in the ocean of space, not just shining with visible light, but whispering in many quiet ways: heat, chemical traces, patterns of movement. These whispers are what astronomers call technosignatures, the measurable, often unintended signs that a technological civilization leaves in its environment. Tonight, we will explore those whispers, one gentle layer at a time, and imagine how they might ripple outward, sometimes so faint that only patient minds and careful instruments could ever notice them. First, consider heat. Any system that uses energy produces waste heat. A city at night, a power plant, a network of satellites, all of these release thermal energy. When you view a planet from far away in the infrared, a world with a lot of technological activity might glow slightly brighter than a purely natural planet at the same distance from its star. This thermal excess is soft and smooth, like the slow warmth that remains on a shoreline after sunset. For distant observers with sensitive enough infrared eyes, a planet's unusual warmth could be a clue that something engineered is happening on the surface. Next, imagine the air itself. Our industrial processes create chemical fingerprints, gases and molecules that would not normally be abundant in a planet's atmosphere. Modern Earth carries traces of chlorine-bearing and fluorine-bearing molecules, certain synthetic compounds, and even complex organics that are unlikely to arise in great quantities through geology alone. From afar, a steady, unexplained presence of such molecules in a planet's atmosphere could read like a quiet signature of industry, an odd scent on the breeze that says, something out of the ordinary is unfolding here. There is also the subtle glow of night-side illumination. On a world blanketed in city lights, the dark hemisphere might not be entirely dark. When a planet passes in front of its star, careful observers can measure the tiny change in brightness, and even infer how light is distributed across its surface. A planet whose nights shine more than expected could reveal the presence of large-scale organized lighting. Imagine the pattern of continents traced in soft luminescence, a faint necklace of lights reminding a distant watcher that life here organizes itself into communities. Beyond air and light, consider engineered materials and unnatural patterns. Large-scale structures in orbit, rings of satellites, dense belts of debris, or colossal solar collectors could scatter or block starlight in ways that stand out from natural rings or clouds. A star dimmed in a very specific way, or a transit that shows geometric repeating shadows, could suggest artificial constructs. These are not spectacles of fireworks, they are more like the steady geometry of an arranged garden, with straight lines and repeating motifs that nature rarely produces by accident. One of the most evocative ideas is waste heat on a much grander scale. A civilization that harvests a star's energy might radiate that collected energy as mid-infrared emission. To a patient astronomer scanning the sky, certain stars might appear to have a faint, persistent halo of heat that cannot be explained by dust or young stellar activity. This kind of infrared excess is a gentle, persistent pulse, the byproduct of industrious engineering writ large. Now let us bring these technosignatures back to the idea of attraction. Why would a technosignature draw attention? Because for any curious observer or autonomous probe, these signs are evidence of complexity. Heat, unusual molecules, coherent light patterns, or structured orbital debris are markers that a world hosts processes beyond simple geology or atmospheric chemistry. In a cosmos where most bodies are inert and unremarkable, such anomalies would naturally appear on lists of places worthy of further study. To make this more intimate, imagine a quiet observatory far from a young star. A cataloguer notes a planet whose atmosphere contains a surprising molecule, one that doesn't fit models of the planet's natural chemistry. They file the finding into a registry, candidate technosignature. Centuries pass. Machines of observation grow more capable, and eventually an automated scout is dispatched. Not like a dramatic spaceship from a movie, but a deliberate, energy-efficient mission built to take samples, to record, to learn. The scout travels along slow, patient paths, perhaps using gravity assists and precise long-term planning. If the scout needs to save energy, it might choose to hitch a ride on a passing natural object, an icy rock, a comet, or even something like 3I/ATLAS, and let the universe carry it closer to the target. This is the quiet, efficient logic of long-range exploration. Another angle to consider is the byproduct of our own near-Earth activity, orbital debris. Human-made material encircling a planet can form structures and scattering profiles unlike natural rings. A dense cloud of tiny reflective fragments could produce a recognizable scattering signature in reflected light. For an outside observer, a planet with an unusually dense ring of debris around it might stand out, like an unexpected wreath around a lamppost. Over time, if many civilizations create dense orbital environments, the galaxy might be studded with these faint wreaths, offering a map of industrious, spacefaring worlds. There's also an increasingly practical source of technosignatures to ponder: beamed energy for propulsion. As we dream of launching light-driven sails and accelerating small probes with lasers, the beams themselves would be visible as focused, transient spikes if an observer happened to lie along the beam's path. These beams are not subtle. When active, they would briefly make a system much brighter at certain wavelengths. Even if the beams are intended for local use, their brief, brilliant passages across a narrow cone of space could act as flares that chart the location and technological maturity of a civilization. And finally, let us touch on the more conceptual technosignatures, intentional messages or symbols carved in the timing of transits or engineered modulation of a star's brightness. A civilization could, in principle, prime their star with subtle, repeating alterations to make a pattern, a cosmic semaphore that says in effect, we are here and we can shape our environment. Whether any society would choose such a noisy announcement is an ethical question we will explore in later chapters. For now, it is enough to know that such possibilities exist in our theoretical toolkits. To help ground these ideas, here is a quiet vignette. On a slow night, an archivist in a remote data center scrolls through decades of spectral surveys. An algorithm flags an oddity: a small planet with an unexpected band of long-wave infrared emission and traces of unusual molecules. The archivist marks it as a candidate and, out of habit, sends a note into the collective network of observers. Years later, a fleet of tiny probes built by a distant science consortium departs, choosing the most energy-efficient route. One probe, seeking to conserve precious fuel, nudges itself into a slow interception course with a passing interstellar pebble, and when conditions align, latches onto it, a subtle hitchhike across the dark. That pebble becomes a messenger, a carriage, and perhaps an unintended cataloguer of another world's story. As you rest into this thought, feel the slow sweep of curiosity that connects us to other minds, not through frantic calls, but through methodical notes left in the margins of stellar catalogues, through faint thermals and chemical signatures that whisper our existence to whoever cares to listen. Imagine, too, how our own actions might one day make that whisper louder. More light at night, more engineered molecules, more concentrated beams. Each choice nudges the amplitude of the signal we cast into the dark. In the chapters ahead, we will follow these threads deeper. We will ask how likely it is that technosignatures attract natural or artificial visitors, examine concrete mechanisms for hitchhiking on interstellar objects, and explore the ethics and consequences of deliberately amplifying our cosmic visibility. We will also bring you stories, imagined and plausible, of how distant watchers might interpret our signals, and of how patient, slow exploration could one day reach us. For now, let the image of a warm, gently glowing planet settle in your mind. Picture the soft infrared halo, the faint ordered glow of city lights, and the delicate chemical trace riding on the breeze. Breathe slowly and allow the thought of being noticed, not as an alarm, but as a quiet acknowledgement, to ease into your awareness. Chapter 5: Hitchhikers of the Void. How natural rocks could carry a message. Imagine a long, slow post that travels the ocean, not made of paper and ink, but of ice and stone. It floats through cold currents, picks up salt and carries traces of distant shores. In the silent ocean of space, small natural bodies, pebbles, comets, and icy fragments can play a similar role. Tonight, we'll follow those quiet couriers and gently unravel the ways a simple rock could become a carrier of information, a slow bridge between distant civilizations. First, picture an interstellar pebble drifting through the darkness. It has no engine, no will. It moves according to the gravity and pushes of the environments it passes through. Yet there are many physical processes that can alter the path of a small body over time. One of the gentlest is the pressure of starlight. Photons striking a surface impart a tiny push. Over centuries, for very small and light objects, this pressure can subtly change their trajectories. Imagine the pebble as a tiny sailboat nudged by a barely felt breeze, almost imperceptible, but persistent. Another natural force is related to heat. When sunlight warms one side of an irregularly shaped rock, molecules lit on that side can slowly escape as gas, causing a slight thrust. This is most visible in active comets when they approach a star. The outgassing creates tails and can change their rotation or path. For a passive object, these minuscule pushes add up like a patient clock tapping away the seconds, altering where the object will drift over millennia. Then there is gravity, the great sculptor of orbits. A passing planet can act like a gentle hand on a wandering pebble, reshaping its path with a careful tug. Astronomers call these maneuvers gravity assists when deliberately used by spacecraft. In nature, they simply happen. A small morsel crossing near a giant planet can be bent onto a new trajectory, perhaps slingshot toward the inner system, or tossed outward into a deep, slow orbit. If you imagine a clump of pebbles passing through a stellar neighborhood, each close encounter is a chance for the cosmos to redirect their journeys in subtle ways. Now, let us calm our thoughts and consider how an intelligent actor, a faraway civilization or an autonomous probe, might take advantage of these natural tendencies. Building a large, fuel-hungry engine to push a probe across light years is expensive in energy. Instead, an efficient strategy is to conserve energy by riding what already moves. A tiny probe could be designed to latch onto a passing object, to anchor itself within a groove in the rock, to tuck into a cavity beneath an icy crust, or to magnetically cling to a metallic fragment. Once attached, the probe becomes a passenger on a trajectory shaped by gravitational nudges, radiation pressure, and occasional outgassing, all essentially free propulsion in cosmic terms. This hitchhiking idea has a quiet elegance. A probe that blends with natural debris need not advertise its presence. It can travel patiently for centuries or millennia, waiting for the right alignment to bring it close to a target. The host rock offers shielding from cosmic rays, thermal insulation, and, importantly, a means to move without burning fuel. From a distance, a rock that has been used in this way looks ordinary. To observers without close inspection, the difference may be indistinguishable. there are practical design considerations that make hitchhiking plausible. A probe intended to survive long trips must be small, robust, and low power. Electronics would be simplified, with long-life memory storage and passive sensors designed to wake only under certain conditions. For example, when the temperature pattern indicates proximity to a star, or when the local magnetic environment changes. Power could be scavenged from faint radioactive decay, thermoelectric generators that use temperature differences, or from micro-solar panels that deploy when the rock draws close to a sun. The goal is quiet endurance, not flamboyant activity. Let us imagine one such device. It could be less conspicuous than a grain of sand on a shoreline. Centuries ago, a distant observatory noted a narrow band of focused energy emanating from a small star system. Intrigued, they launched tiny scouts, simple machines built to endure, each no bigger than a fist. One of these scouts found a passing interstellar pebble, and, using a minute grappling arm, embedded itself within a small crevice. The pebble continued its ancient route, nudged by unseen forces, and eventually passed through another system, carrying the quiet record of distant curiosity. The mechanics of capture can be elegantly efficient. A probe could exploit differences in thermal expansion to wedge itself more tightly into a cavity as temperatures change. It may release small amounts of lubricant or adhesives at precise moments to secure attachment. Passive sensors would remain dormant, collecting only the most relevant data, magnetic field variations, particulate composition, and local radiation levels, until a pre-programmed trigger woken by time, temperature, or proximity occurs. When the host rock approaches a target of interest, the probe could emerge, unfurl a sensor array, or deposit nanostructured markers that alter the surface reflectivity in subtle, detectable ways. We should also consider the possibility of deliberate modification. A civilization interested in sending information cheaply might etch microscopic patterns into a surviving fragment surface, a slow, durable encoding that resists erosion in space. These patterns would not be obvious at a glance, but they could be found by a careful scanner, like reading a faint inscription on a weathered stone. Alternatively, small payloads containing data in highly stable forms, crystalline lattices, encoded minerals, or protected optical disks, could be embedded within a rock, a cosmic time capsule waiting for discovery. As we explore these mechanisms, it's important to stay grounded. There is no direct evidence that such hitchhiking probes exist. The scenarios we describe are plausible pathways consistent with known physics, and they hint at how an otherwise ordinary interstellar object could harbour extraordinary secrets. This is a gentle thought to carry. The universe's ordinary things might be hiding unusual histories. To bring the idea home, let's relax into a quiet vignette. A shepherd rock enters a new stellar neighbourhood after a long, cold drift. Local radiation wakes dormant electronics. A tiny probe unfurls like a slow blossom, scanning the nearby planets. It records faint radio leakage, the spectral fingerprints of atmospheres, and the sing-song pattern of engineered transmissions. The probe compresses its gathered knowledge into an ultra-stable crystal and tucks the crystal back into the rock's heart. The probe then returns to dormancy, as patient and silent as a seed waiting for spring. There's also a practical silence to this approach that is calming to consider. Hitchhiking is not a dramatic arrival with bright engines and loud announcements. It is the opposite. Quiet, economical, respectful of energy, and in tune with the slow rhythms of the cosmos. Such missions, if they exist, would be difficult to detect until we actually intercept and closely examine their carriers. For us, that implies a long-term strategy. Careful surveys of interstellar visitors, patient cataloguing, and a readiness to bring small, fleeting visitors into tighter study. As you rest with this thought, imagine the countless rocks passing between stars, each with its own small history. Some are simple and lonely, others may be layered with traces of distant minds. Our own future choices, whether we leave engineered markers, whether we deploy small, durable artifacts into interstellar space, may add new layers to this quiet archive of the galaxy. If you close your eyes, picture a pebble's slow, graceful arc, starlight sliding over its surface, and remember that even the humblest object can carry a long, patient story. Chapter 6. How we could detect hitchhikers and interstellar stowaways. Imagine the night sky as a calm, watchful ocean. Most of the waves are familiar and gentle, but now and then a foreign ripple crosses the surface, faint, slow, and unlike the rest. Our task tonight is to consider how we, with our instruments and patient curiosity, might notice those ripples and discover whether they carry secrets. Detecting an interstellar hitchhiker is a gentle act of careful listening and focused attention. It begins with patient surveys of the sky, the kind of long, even observation that rewards persistence. Telescopes scan swaths of space night after night, building catalogues of moving points. From that mass of data, we pick out anomalies, objects that move too fast, that come from odd directions, or that behave in ways our models do not predict. This is the same cadence by which we first found objects like 3I/ATLAS, softly at first, then with growing certainty as more measurements arrive. One of our first tools is the light curve, the pattern of brightness an object shows as it rotates and tumbles. An irregular brightness variation can tell us about shape and rotation. A long, smooth periodicity might imply tumbling like a slowly rolling log. Abrupt changes could indicate shedding of dust or outgassing. For a hitchhiker hiding within a rock, light curves may be mostly ordinary, but careful analysis can reveal tiny consistent deviations. A shadow that repeats at a specific phase, a reflective patch that appears like a heartbeat. These small repeatable signatures are the tracks that patient astronomers can follow. Spectroscopy is another quiet, powerful method. When sunlight or starlight reflects off an object, it carries subtle fingerprints of the material it touched. By dispersing that light into its component colours, instruments can identify the presence of metals, silicates, ices, or exotic minerals. If a rock has an embedded artificial component, a crystalline lattice, a polymer residue, or a highly polished surface, the reflected spectrum may carry telltale signs. These anomalies are rarely dramatic. They're instead delicate notes in a complex chord, requiring high signal-to-noise observations and meticulous calibration. For the gentle listener, spectroscopy tells the rock story, where it has been, what it carries, and what it might hide. Radar and radio observations add another quiet dimension. When we bounce radio waves off close objects, we can measure shape, surface roughness, and rotation with exquisite detail. Radar has been used to map asteroids in our own solar system, revealing ridges, boulders, and unexpected hollows. If an interstellar visitor passes close enough, a well-timed radar campaign could reveal cavities, artificial reflectors, or unusual internal structure. The echo returned from a rock is like a whispered reply to a polite question. Small changes in the echo can mean a lot. Thermal imaging, the study of an object's heat signature, can yield subtle clues too. A rock warmed by sunlight will re-radiate that heat as infrared light. If a section of the surface behaves differently, warming or cooling in a way that defies expected thermal inertia, it could indicate an embedded object with distinct thermal properties. Even more intriguing, a probe with internal power sources might create a faint, steady thermal anomaly when its host comes near a star. Detecting such a whisper of warmth requires patient instruments and a willingness to let small signals grow in confidence over repeated observations. High-resolution imaging, when possible, is the most intimate way to learn. Space missions that rendezvous with comets and asteroids have transformed our understanding of small bodies, revealing pebbles, fractures, and textures we never suspected from Earth-based observations alone. For interstellar visitors, a close-up image could be transformative. It might show a cavity sealed with a thin crust, a pattern of micro-etchings, or a surface unusually smooth for a natural rock. But such missions require precise planning, energy, and time, gentle investments for potentially great rewards. There is a quiet art to interception that is worth describing. Suppose astronomers identify a candidate interstellar object entering our system. A measured, calm response could be to launch a fleet of tiny chaser probes, low-cost, solar sail-driven microcraft, each carrying a complementary sensory suite. These craft do not roar across space like cinematic shuttles. They drift, deploy, and gradually close the distance using carefully timed gravitational assists and slow pushes from light. Their arrival is a quiet meeting, a few grams of hardware unfolding delicate sensors to whisper alongside a billion-ton rock. The probes would photograph, sample, and, if feasible, anchor and return microscopic samples, or relay in situ analyses back to patient Earth. Another less flashy yet elegant approach is capture nets, a concept where a trailing spacecraft deploys a large, thin membrane to gently snare a small body and bring it into a controlled orbit for study. This is not forceful. It is a soft, controlled embrace designed to minimize alteration of the captured object's structure. The membrane and spacecraft form a cradle, allowing scientists to study the visitor in a stable environment and, crucially, to look for any signs of embedded technology. We should also think about laboratory work, the methods we would use to analyze a returned sample. If a rock carried an embedded device, detection might come from finding materials that do not match the expected cosmochemical signatures. Ultra-stable isotopic compositions, precise crystalline structures, or minute traces of manufactured polymers could all betray artificial origins. Microscopy, mass spectrometry, and X-ray diffraction. These calm, methodical techniques would reveal whether a tiny probe lived within the stone's heart. A probing question softens the night. How do we prioritize which visitors to chase? Not every passing pebble is interesting, and our resources are limited. The answer lies in triage. Speed, trajectory, brightness, and spectral anomalies guide the decision. A slow, large object that displays unusual spectral features or thermal behavior becomes a higher priority candidate than a rapid, dim speck. This selection is not rushed. It is deliberative, balancing curiosity with prudence. Finally, let us hold a small human vignette in our minds. Picture a future research team in a quiet control room, soft light, coffee cooling beside a keyboard. An automated pipeline flags a twilight object whose light curve has a subtle, repeating ripple. The scientists lean in, collectively holding their breath in the mildest way possible. There is no alarm, only careful excitement, an ancient practice of listening deeply. They plan a series of observations, tuning instruments and aligning radar windows. Days become weeks. The data accumulates, and the whisper becomes clearer. It is the kind of slow discovery that rewards patience, and when the first close-up image finally arrives, the room is not raucous, it is reverent. They have found something extraordinary, but it revealed itself in the quietest manner. A tiny, deliberate anomaly inside a weathered rock telling a long story. As you sink further into ease, let this chapter's image linger. Instruments tuned like patient ears, telescopes tracing slow arcs, tiny probes unfurling like flowers. Detecting a hitchhiker is an act of careful attention, not force. It is the universe inviting us to listen more closely, to practice the long patience that encounters across light years require. Chapter 7. To speak or not to speak. The ethics of signalling the cosmos. As we continue our gentle voyage through these possibilities, let us pause and consider a question that folds science into philosophy and policy. Should we announce ourselves? Does the universe deserve to hear from us? Or is silence the wiser path? Tonight, we explore the ethics of signalling, the careful debate between those who wish to raise a hand and say, "We are here," and those who counsel patience and quiet observation. Begin by picturing two quiet rooms. In the first, a single researcher sits before a powerful transmitter, composing a message meant for the stars, a concise story of who we are, numbers, images, music, and a gentle greeting. The transmitter hums, the beam narrows, and for a brief moment a slender thread of human intention leaves Earth, heading into the dark. In the second room, an international council of scholars, ethicists, and citizens gathers by faint lamplight, weighing whether it is right to send that thread. Both rooms exist in the same world. Both choices are born of curiosity, care, and caution. The debate about active SETI, intentional messaging to extraterrestrial intelligence, centers on a few calm, key concerns. On one hand, there is the simple beauty of connection. Proponents say that announcing ourselves could catalyze contact, accelerate knowledge exchange, and fulfill a deep yearning for cosmic friendship. The action is framed as an act of openness, of offering to share our science, our art, our story. It is hopeful, generous, and deeply human. On the other hand stands the argument for prudence. Some scientists caution that broadcasting identifiable signals could invite unknown consequences. Even if the likelihood of an immediate response is vanishingly small, the ethical consideration extends beyond probability. It asks whether it is right for a species to make a decision that could, in theory, affect all future generations without broad consent. This is not merely fear of hostile civilizations from stories. It is an appeal to collective agency and the recognition that some decisions ripple across centuries. To explore this calmly, let us slow our thoughts and categorize the concerns with clarity. There are pragmatic, technical concerns, the content of the message, the power and direction of transmissions, and who decides on the targets. Then there are cultural concerns, whose language, values, and images represent humanity. Finally, there are existential concerns. What right do we have to expose our existence to unknown observers, and how should we balance curiosity with caution? From the technical side, careful minds propose protocols. Messages could be low bandwidth and scientifically informative, designed to be unambiguous and to minimize misinterpretation. Transmission could be limited in scope and time to reduce unintended broadcasting. Targeting could be conservative, aimed at star systems with long-lived sun-like stars or at objects already catalogued as interesting, rather than sweeping indiscriminately across the sky. These are engineering-minded mitigations, modest steps that acknowledge risk without succumbing to paralyzing fear. From the cultural side, the question grows more soulful. Who speaks for Earth? Our species is not a single voice, but a chorus of languages, histories, and beliefs. Some propose inclusive, multicultural committees to design messages, ensuring that a wide range of human perspectives is represented. Others gently point out that any message will inevitably be partial. It will reflect choices and values, and those choices themselves are an ethical act. The process of deciding thus becomes as important as the content. Deliberation can be a moment of shared reflection about who we are and who we hope to be. Then there is the notion of consent across time. If a message might one day alter the trajectory of civilization through contact by becoming a historical record or by catalyzing new technologies, is it right for current generations to decide for those to come? This element invites us to practice a more patient ethics, one that values stewardship and includes the voices of future stakeholders. It is a humbling stance, rarely demanded in ordinary life but eminently reasonable when the stakes are cosmic. Alongside the debates, it's a quieter thread, the idea of defensive silence. Some advocate for a policy of listening, gathering evidence and understanding our cosmic neighbourhood before making bold announcements. This posture is not born of cowardice, but of humility. It treats the galaxy as a shared environment where actions are best taken with careful study and broad agreement. To illuminate these issues with a gentle vignette, imagine a coastal village centuries ago deciding whether to light a bonfire at night to signal across the bay. Some villagers say the fire will attract friends and traders. Others fear it will draw storms or raiders. They compromise. They build low, controlled beacons that can be extinguished, and they agree on a watch rotation. In modern terms, we might think of these beacons as limited, reversible transmissions, a way to test, to learn, and to keep options open. Another practical and calming approach is the idea of phased escalation. Start small and reversible. Public, low-power broadcasts that test how our signals propagate and whether they leave signatures easily detectable at modest distances. Combine that with robust listening and transparent international oversight. If evidence accumulates that the cosmos is quiet or indifferent at the scales we can reach, deliberate escalation can be reconsidered with broader input. This staged method respects both curiosity and caution. It keeps the door open while avoiding hasty acts. There is also an emotional balance to hold. Humanity's urge to reach outward is a deep, generative impulse. For many, silence feels like a denial of part of ourselves, a quieting of the creative voice. For others, the restraint is an expression of care for something larger than immediate curiosity. The ethical task, then, is to find a path that honours both impulses, to explore and to protect, to speak and to listen, to do so transparently and with humility. Finally, consider the long-term norms we might craft. International agreements, akin to environmental treaties but directed toward the cosmos, could guide how we transmit, what we send, and who decides. Public education and global conversations could shape consensus over time, rather than leaving these decisions to small, technically proficient groups. These norms would be soft, patient architectures, the calm scaffolding that brings collective wisdom to bear on choices of cosmic significance. As you rest into these thoughts, visualize an assembly of people from many places, elders, students, artists, engineers, sitting in a ring under a night sky. They listen to one another with care, speak with restraint, and decide together that any act of broadcasting will be thoughtful, reversible, and informed by science and ethics. Picture that image as a model for our future civic responsibility. Not a single shout into the dark, but a conversation that unfolds slowly, respectfully, and with a deep sense of shared stewardship. In the chapters to come, we will explore related terrain, the practicalities of a stage transmission program, historical lessons from how humans signaled across oceans, and the quiet technological designs that minimize risk while enabling discovery. For now, let this chapter temper your curiosity with a calm sense of responsibility, the gentle wisdom that sometimes the bravest act is to listen first. Chapter 8. The Fermi Factor. Probability, scale, and why visitors might be rare. As we continue, let us sit with a quiet, thoughtful question that has accompanied stargazers for decades. If the galaxy is vast and old, why do we see so little that indicates other technological civilizations? This is the gentle heart of the Fermi question, a calm riddle about probability, scale, and patient time. Tonight we will unpack the layers of that puzzle in simple, understandable terms, without rushing, so that the vastness of space feels less like a void and more like a slow, careful landscape we can walk through in our minds. Begin by imagining a great library with shelves that extend farther than your eye can see. Each shelf is a region of the galaxy. Each book is a civilization. Some books are thick and long-lived, others are brief pamphlets, and many shelves remain empty. The question is, how many books are there, and how bright are the spines? The answer depends on many things: how often life arises, how often intelligence follows, how long technological civilizations last, and how loudly they signal while they do. To make sense of this without math-heavy steps, we can think in 4 gentle dimensions: abundance, visibility, longevity, and distance. Abundance. How many civilizations exist? The universe is large and old, but the conditions for life and intelligence are specific. Favourable planets must be in the right temperature range, have the right chemistry, and remain stable long enough for complexity to develop. Even if life is fairly common, the step from simple life to technological, space-aware intelligence could be rare. So abundance may range from many quiet, isolated pockets to very few bright centres. Imagine a meadow dotted with a few wildflowers, beautiful but not everywhere. That distribution matters for how likely an interstellar visitor might originate nearby. Visibility. How detectable are civilizations? Even if many civilizations exist, most may choose or happen to be quiet. Some may produce vast techno-signatures, bright beam transmissions, star-spanning engineering, or dense orbital structures, while others emit only faint, hard-to-detect whispers, minor radio leakage, small waste heat excesses, or tiny atmospheric traces. Our ability to notice a civilization depends not only on how widespread it is, but on how loudly it advertises itself. In the library metaphor, visibility is whether a book's spine is gilded and obvious, or wrapped in plain paper. Longevity. How long do they last? A civilization that endures for millions of years has far more opportunities to be noticed than one that exists for just a few centuries. Long-lived civilizations can develop broad, slow strategies of exploration and leave long-lasting markers. Short-lived ones may never get far beyond their home world. Longevity stretches or shrinks the time window in which other civilizations might intersect with their signals or probes. Distance and timescale, the tyranny of light travel. Space is vast in both space and time. A signal or probe takes years, centuries, or millennia to cross even nearby star systems. If a civilization's window of activity is short relative to these travel times, messages and probes may simply miss one another. Imagine 2 ships that flash their lanterns from different horizons. Unless they keep repeating or look in the right direction at the right time, they may never see each other. When we ask whether we might be noticed, or whether we might have summoned an interstellar object, these 4 dimensions work together. Even if a distant civilization observed unusual beamed activity near our star, they would still face the practical task of sending a probe across immense distances, waiting patiently, or crafting missions that could survive long idle periods. The most energy-efficient strategy might be to send tiny, durable scouts, and rely on natural objects to do the heavy transport, the hitchhiking idea we explored earlier. But even then, the odds depend on how many senders exist, how persistent they are, and how aligned their paths are with ours. Let us gently explore the concept of capture probability, a simple way to feel the geometry of chance. A rock passing near a planet can be nudged and captured only within certain windows and alignments. The region in space where a small object can be diverted toward a planet, its effective capture cross-section, is relatively small when compared with interstellar volumes. So even if many pebbles cross a system, only a tiny fraction will find trajectories that bring them close enough to be captured or to deliver a payload deliberately. This is not discouraging. It simply reminds us that encounters are rare and often require patient timing. Another comforting thought is that rarity does not equal loneliness forever. The galaxy evolves slowly. Rare events become more likely given enough time. A patient civilization with a long planning horizon could orchestrate low probability, high impact missions by spreading many tiny scouts across the galaxy, or by sending probes that float for epochs until conditions align. These strategies favour endurance over instantaneous glory. The Fermi question also invites reflection on our observational limits. We have only recently developed the instruments needed to detect faint technosignatures or slow-moving interstellar visitors. The night is enormous, and we have lit only a few lamps. It is possible that other civilizations are out there, their signals dim, their probes stealthy, and their visits rare. Not because they do not exist, but because our instruments and our patience are still catching up. To ground these ideas in a calm story, imagine a slow librarian of the galaxy, an automated archive that catalogues energy spikes and odd orbits. The librarian receives a faint entry centuries ago, a narrow beam detected by a parochial observatory in a star cluster. The archive marks it, and over millennia the signal draws attention from a consortium of distant systems. They assemble a fleet of tiny scouts, but energy conservation and the geometry of space lead them to send many more scouts than they can directly aim. Most drift into the void, a few hitch rides on passing rocks. One of those rocks, after a patient travel of epochs, intersects our neighbourhood and becomes a quiet messenger. The process is slow, methodical, almost bureaucratic, not an invasion, but an archivist's long-term project to cross-reference interesting entries in the cosmic catalogue. Finally, this chapter invites an emotional calibration. The Fermi question is not a threat or a promise. It is a framework for humility. It asks us to accept that the universe operates across scales far larger than our everyday lives, and that meaningful contact, if it occurs, will likely be patient, quiet, and rare. This perspective can be soothing. It frees us from the clever tricks that reduce cost, and how those constraints shape the kinds of probes that could plausibly arrive at our doorstep. We will also examine how different types of civilizations might choose different strategies, some bold and conspicuous, others stealthy and archival. For now, hold the image of the library in your mind. Sparse shelves, patient archivists, and a few slow, shining spines that, with time and care, may one day reveal their stories. Chapter 9. Engineering the Patient Fleet. How small, durable probes could travel for millennia. Tonight we turn our attention to the quiet workhorses of a long-distance curiosity. The probes that do not rush, the small machines designed to endure. If civilizations choose to explore across the gulf between stars, the most elegant designs are often the simplest and most patient. In this chapter, we will gently unpack how engineers might build tiny, resilient scouts, what constraints shape their form, how they power themselves, and the ways they survive and communicate across epochs. Picture a fleet of pebbles glinting in the dark, each as modest, purposeful, and built to wait. Start with the most basic engineering truth. Mass is expensive. In space travel, every extra gram multiplies the energy required to move it. That simple fact pushes clever designers toward minimalism. The smallest probes, often called wafer-scale or pebble probes in concept, strip functionality down to essentials: robust sensors, efficient data storage, a reliable trigger to wake them when conditions are right, and a survival architecture that tolerates damage. Think of them as durable notebooks rather than full laboratories, built to record and preserve, not to host complex expeditions. Power is the next silent constraint. Traditional rockets carry tanks of fuel and powerful engines. Durable, cheap scouts cannot. Instead, long-duration probes rely on low-power strategies. A few calming options exist. Radioisotope microgenerators, tiny sources that convert the slow decay of radioactive isotopes into steady low-power electricity. They are quiet and long-lived, like a small ember that never quite dies. Thermoelectric harvesters, devices that extract power from temperature differences. If a host rock warms as it approaches a star, the probe can exploit that gradient to generate bursts of energy. Microsolar arrays, deployable feather-like panels that unfold when sunlight becomes available. These are used sparingly, conserving energy for key moments. Energy scavenging, harvesting transient electromagnetic noise, cosmic rays, or tiny mechanical motions inside a host rock. These methods yield only minute power, but can sustain passive monitoring and wake-on-trigger capabilities. Robustness matters more than sophistication. Electronics must be radiation-hardened, with memory redundancy and error-correcting codes to survive exposure to cosmic rays. Mechanical parts are minimized. Moving parts are failure points. So many designs favor solid-state sensors and non-moving optical systems. Passive shielding, embedding the probe within rock or behind layers of regolith, provides thermal buffering and protection from micrometeorites. Imagine a tiny instrument encased like a seed within a nut, nature's shell doing much of the protective work. Communication is both a desire and a burden. Sending data across light years requires power and a sharp focus. One calm strategy is store and forward. Probes collect and compress data, then wait to come within range of a relay or a listening post, or attempt to hitch to an object likely to pass nearer a civilization that can receive. Another strategy is to emit short, infrequent bursts using tiny, highly directional transmitters, whispers aimed only when the probe has amassed something truly valuable, thus conserving energy while still offering the chance of contact. The practical reality is that continuous high-bandwidth transmission is rarely feasible for Pebble-class scouts. Patience and clever scheduling replace continuous chatter. Redundancy is gentle insurance. Instead of one large craft, a patient program might send thousands or millions of tiny units. Most will be lost, eroded by interstellar hazards, or never find an advantageous trajectory. But a few survivors, the statistical winners, will succeed. This is an approach borrowed from nature. Scatter many seeds, and a few will land in fertile soil. It is cost-effective and robust over long time scales. Consider the propulsion and travel architectures that enable patient fleets. Passive drift. Let objects coast on natural orbits and currents, attaching probes to bits of debris that already move between stars. Light sails and beamed propulsion. Use focused light, lasers or microwaves, to push ultralight sails to a fraction of the speed of light. These systems can accelerate small craft without carrying propellant, but they require substantial infrastructure at launch. Once launched, sails glide on quiet, steady pushes. Gravity-assisted routing. leverage the gravity wells of stars and planets to redirect trajectories economically, designing trajectories that trade time for energy. Hybrid strategies combine beamed pushes for initial injection with passive drift for the long cruise, and then light touch maneuvers close to targets. All of these strategies favour smallness and patient travel times. A probe designed to drift for millennia must be built like a monument, simple, reliable, and tuned for survival rather than immediacy. Another important engineering theme is stealth versus visibility. Depending on intent, designers may minimize an instrument's electromagnetic signature to avoid detection, or conversely equip it with simple reflective elements to make it learnable by the target civilization. Both approaches are quietly reasonable. A stealthy probe trusts patient discovery by close inspection. A beaconed probe gently signals its presence when conditions allow. Each design choice shapes how an interstellar visitor would be perceived if found. We should also consider the software that runs these patient machines. Unlike the instantaneous AI we imagine in movies, probes for epical voyages would run conservative, fault-tolerant code. Their intelligence would be centered on diagnosis, efficient data compression, adaptive sleep modes, and a handful of heuristics for when to wake and transmit. They would prefer simple, transparent decision trees over opaque learning systems that may drift unpredictably over centuries. Reliability and predictability trump cleverness in the long haul. Packaging for longevity is an art. Data must be encoded in stable media, crystalline lattices, chemically robust polymers, or encoded atomic arrangements that resist decay. Physical inscriptions, etched at micro or nanoscale, provide another durable archive. Patterns in a metal lattice or in mineral layers that survive radiation and impact. These are the cosmic postcards of explorers, dense, slow-to-read deposits that can be analysed long after the probe's active electronics have failed. Now let us settle into a small, illustrative story to make these engineering choices feel tangible. Imagine a project named Dawnseed, a modest, international effort conceived not as a triumph, but as an exercise in patient stewardship. Engineers craft thousands of wafer probes no larger than a postage stamp, each with a tiny data archive, a passive sensor suite, and a microconnector designed to lodge into porous rock. They mass-produce these wafers and then carefully attach them to small, fast debris ejected by a modest launch into interstellar space. Some wafers are pushed by beamed lasers to reach the outskirts of nearby stellar systems. Most are left to drift. Centuries pass. A handful finds their way onto slow, elongated paths that bring them close to distant worlds. One wafer, carried inside a larger pebble, passes near a sun and warms. Its thermoelectric generator awakens. It records the composition of the nearby planet's atmosphere and compresses the finding into a tiny crystalline archive. The probe waits until a favourable outer conjunction brings it within line of sight of a relay array left by its makers, and then, using a short, highly collimated pulse, it sends the smallest of signals, a tiny packet confirming the data location and time. That signal is brief and discreet, the equivalent of a note slipped under a door rather than a knock down the hall. Dawnseed's design choices, redundancy, simple power, robust packaging, reflect a philosophy. Exploration can be patient, humble, and enduring. It does not need to announce itself with fanfare. Its existence is an exercise in long-term thinking, a trust that knowledge preserved today will find receptive minds in the centuries to come. Finally, consider the ethics that subtly guide design. If probes are meant to be archival, to observe and record without interfering, they should be built to minimize contamination, both biological and cultural. Any sample return strategy must consider contamination risks. The gentle ethic here is non-interference. Leave as little trace as possible while gathering knowledge, so that the visited systems retain agency and integrity. As you rest into these ideas, imagine a quiet hangar where engineers fold wafer probes with careful hands, like origami for futures they will never personally see. Imagine those probes slipping into the dark, patient as seeds, carrying our curiosity in forms small enough to be hidden in a pebble's heart. Their engineering is an exercise in humility, small, resilient, and built to wait. Chapter 10. The Orbital Dance. How interstellar objects can be redirected, captured, or nudged. Tonight, we step into the quiet mathematics of motion, not to overwhelm, but to soften our intuition about how objects move through space, and how a wandering interstellar rock might end up on a path that brings it near us. Think of gravity as a slow, patient choreography. Stars, planets, and small bodies continually exchange tiny pulls. Over long times, those pulls add up and can turn a random wanderer into a guest at our table. This chapter will walk you through the gentle mechanisms that shape those journeys in plain language and with a calm imagination. Begin with the most basic truth. Motion in space conserves energy and momentum. For a rock to change course, something must give it a nudge. Those nudges come in a few familiar and physically modest forms. Nearby gravity, the gentle photon push of light, small jets of gas, and in rare cases direct collisions, each as small on its own but meaningful over centuries and millennia. One of the quietest and most powerful mechanisms is the gravity assist. Picture a pebble approaching a large planet like a ship entering the wash of a great ocean liner. If the pebble passes close enough, the planet's gravity bends its path and can speed it up or slow it down relative to the star. This maneuver is how many of our own spacecraft gain velocity without burning fuel. For interstellar objects, a single, well-timed close pass by a giant planet can alter their trajectories substantially, enough that an object that would otherwise sail past the system instead curves inwards toward the inner worlds, or is tossed outward on a new trajectory. Gravity assists are the cosmos's subtle stewards, efficient, patient, and often invisible until their effects are seen in hindsight. Closely related is the three-body interaction, a more complex dance among three masses. Imagine a small object entering the gravitational influence of a planet-moon pair. In certain alignments, the small body can exchange energy with the moon and the planet, losing a portion of its kinetic energy and becoming bound temporarily or permanently. These captures are typically temporary at first. The object may become a transient satellite, orbiting for some time before perturbations free it again. Sometimes the temporary becomes permanent through additional nudges. The mathematics behind these interactions is rich, but the physical intuition is simple. Three bodies can swap small amounts of motion in ways two cannot, and those tiny swaps can add up. A related gentle phenomenon is atmospheric drag. When a body passes through a thin atmosphere, for instance grazing the outer fringes of a planet's gaseous envelope, it feels friction. Even a small amount of drag can bleed off speed and convert a flyby into a captured orbit. In our solar system, planets with substantial atmospheres can remove a sliver of orbital energy from an incoming object. Atmospheric capture is risky for the incoming rock. It may heat, fragment, or disintegrate. But when conditions are mild, drag can be an effective braking mechanism. Picture a sailing boat slipping into a harbour and dropping anchor. The atmosphere is the harbour's water, slowing motion with patient resistance. Another subtle player is radiation pressure and thermal effects. Photons carry momentum. When sunlight strikes an irregular object, the tiny pressure can, over long times, accumulate into noticeable alterations of trajectory, especially for very small, low-mass objects. There is also a thermal cousin called the Yarkovsky effect. An object warms in sunlight and radiates heat later as it rotates, and that delayed emission creates a tiny thrust. Over many orbits, this thermal push slowly shifts an object's orbit inward or outward. These effects are quiet and slow, but for small bodies drifting across space for millions of years, they are effective sculptors of paths. Tidal interactions can also play a role. When an object passes very close to a planet, the planet's gravity can stretch and stress it. If the tidal forces exceed the object's cohesion, it can break apart into fragments that follow new trajectories, some pieces more easily captured than the original body. The classic image is of a comet pulled apart into a string of pearls, each pearl then tracing its own quiet orbit. Tidal disruption is violent in its mechanism, but can leave behind a calm field of smaller objects that are easier to divert or capture. Now let us gently ask, could human activity influence any of these mechanisms? The answer is yes, but mostly in subtle, local ways, rather than by waving a giant cosmic hand. Here are a few practical influences we might exert. Orbital engineering of near-Earth objects. As our capability to alter asteroid orbits grows, with kinetic impacts, gravity tractors or mass drivers, we might intentionally change trajectories. Those same techniques applied at scale could, in principle, modify the probability that an incoming object is captured or deflected into a safer or more studied orbit. Such operations require energy and care, but they are feasible on human timescales for objects already in our vicinity. Creating deliberate beamed forces. High-power lasers or microwave beams designed for propulsion or asteroid nudging concentrate energy into narrow cones. If used near an incoming object, a beam could impart small but cumulative momentum changes, nudging a path enough to alter a future encounter. The beams themselves would be detectable at a distance if someone looked along the beam line, but their primary use is pragmatic, to shepherd objects rather than summon them. Modifying the near-Earth environment. Large-scale changes to mass distribution, like moving huge amounts of material into particular orbits, or building large orbital structures, subtly alter local gravity fields. These changes are minor compared to planetary masses, but with very precise planning, they could be used as part of long-term debris management or as part of capture strategy design. Importantly, the idea that our activities might summon an interstellar visitor requires recognizing the timescales involved. Light takes years to cross interstellar distances. Probes sent in response to modern beamed signals will arrive centuries or millennia later. If a distant observer noticed our focused energy and launched a probe in response, that probe's arrival would reflect a patient, long-range plan, not an immediate consequence. The cosmos is slow. Actions now echo across long times. There are also probabilistic considerations to hold with gentle care. Redirecting or capturing an object is rarely deterministic. It's a matter of windows, alignments, and small pushes. A slight change in timing can completely alter an outcome. This is the essence of sensitive dependence on initial conditions in orbital dynamics. Small nudges can steer an object into a drastically different future. That sensitivity is both sobering and hopeful. It means small, careful interventions can be effective, and it also means that what appears accidental may, in fact, reflect a chain of small influences accumulated over eons. To calm the imagination further, picture a slow montage. A distant pebble slips past a star, warmed gently on one side. The Yarkovsky effect nudges it over centuries. A passing giant planet redirects its course. A thin atmosphere trims a sliver of speed on the outer edge of a grazing pass. A small fragment detaches and is finally captured into a long elliptical orbit around a habitable world. Each step is modest, and together they form a patient choreography of chance and physics. Finally, consider intentional use of natural mechanics for exploration. A faraway civilization may deliberately design probes to exploit these gentle forces. Rather than fighting gravity and light, they plan trajectories that use them as assistants. Such missions emphasize endurance rather than speed. They are the slow boats of the cosmos, relying on centuries of prediction and small nudges to arrive where curiosity beckons. From our perspective, that means visitors might not arrive as bright, powered ships with roaring engines, but as objects whose arrival is shaped by the subtle, patient mathematics of motion. As you let these ideas settle, imagine the solar system as a calm ballroom where small feet move according to music laid down long ago. Each encounter is part choreography, part improvisation, and the music is a slow combination of gravity and time. The path that brings a wandering rock near to us is a long story told in faint pushes and patient turns, an orbital biography written in the language of physics. Chapter 11. What clues might 3I/TLAS hold on its surface and inside? Tonight we draw very close, not in person, but in imagination, to the silent surface of a visitor like 3I/ATLAS. What marks does it carry from its long journey? What tiny anomalies could betray a story of stowaways, deliberate modification, or simply an unusual natural history? This chapter is a calm, methodical checklist of the signs scientists would look for and how those signs might be interpreted. As always, we remain gentle and patient, letting each small clue gather into a broader picture. Begin with the surface texture. From a distance, an interstellar rock appears as a point of light that brightens and dims. Up close, its skin tells the first part of its story. Natural processes leave characteristic textures, micrometeorite pitting, crystalline frost layers, regmaglyphs like thumbprints formed by ablation, or layers of dust accumulated in a quiet region of space. An embedded artificial object, however small, may produce local anomalies. A patch where erosion is different, an area of unusual smoothness, or a section with reflective facets that catch the light in an atypical way. Finding such a patch is the kind of quiet surprise that sparks careful follow-up. Next, consider spectral fingerprints. When starlight reflects off a surface, it carries an imprint of the materials it touched. Spectrometers can identify minerals, ices, metallic compounds, and organics. To the patient observer, a mismatch between expected cosmochemical composition and local measurements can be revealing. For instance, if a small region shows a concentration of highly refined alloys or isotopic ratios inconsistent with known stellar processes, it suggests processing, either by geological processes we don't yet understand, or by manufacturing. Even tiny traces of synthetic polymers or rare earth element distributions could hint at artificial origins. These are faint notes in a complex symphony, but they can be definitive when played back carefully in a lab. Magnetic anomalies are another subtle clue. Many manufactured devices use metals with particular magnetic properties, or include electrical components that leave residual magnetization. A local region with a magnetic signature that differs markedly from its surroundings could indicate embedded hardware. Measurements taken at different distances and angles, with magnetometers, can map these anomalies and guide further inspection. The magnetometer reads like a patient wrist pulse, steady until it reveals an unexpected flutter. Isotopic ratios are an especially telling signature. Natural processes produce predictable ratios of isotopes, the various forms of elements that differ only in mass. Industrial refining or biological activity can shift these ratios in characteristic ways. For example, certain processes fractionate carbon, oxygen, or noble gases in ways that depart from typical cosmochemical expectations. Detecting such anomalies in a rock sample is like finding a linguistic dialect in a long-forgotten letter. It hints at a local history not written by simple physics alone. We mustn't overlook micro-etchings and patterned surfaces. Manufacturing leaves telltale marks, repetitive machining striations, microlattice regularities, or etched patterns that repeat at small scales. These would be subtle and require high magnification imaging to detect. Imagine an archaeologist finding micro grooves on pottery. The grooves reveal technique and intent. Similarly, tiny etchings on a stone may encode information, timestamps, or simple identifiers intentionally designed to persist through space weathering. Another soft possibility is non-natural radio or electromagnetic artifacts. Even dormant electronics can present awake, tiny dielectric inclusions that resonate at specific frequencies, or conductive traces that alter the way the rock scatters radio waves. Radar studies and active probing with a variety of frequencies could reveal resonances inconsistent with purely rocky compositions. These echoes are like a faint tuning fork struck by a passing breeze, subtle but distinct. Porosity and internal cavities deserve a patient look. Many meteoroids and comets have porous interiors, pockets where volatiles once were. An embedded device might be nestled within such a cavity, shielded by surrounding material. Ground-penetrating radar from a close spacecraft, seismic probing if a lander can tap the surface, or carefully planned impactor experiments could reveal voids and heterogeneities. The delicate work is to probe without destroying. Think of a doctor using imaging to peer inside without an incision. If a probe were present, how might it be powered or preserved? Very small devices rely on long-lived energy sources, radioisotope decay, sealed batteries with low leakage, or passive systems that maximize long sleep intervals. Selecting the right instruments for detection means looking for telltale decay heat, micro-radiation patterns, or thermally anomalous spots that do not match the environment. Detecting a tiny, consistent thermal excess would be a calmed, patient triumph. A low hum in a world otherwise dominated by cold. Contamination control is an important practical layer, and one that reflects humility. If humanity plans to visit interstellar objects, we must ensure we do not confuse our marks for alien ones. Rigorous planetary protection protocols are essential. Sterilized spacecraft, careful documentation of what materials we carry, and redundant cross-checks to distinguish indigenous anomalies from human-made contamination. This is not paranoia, it is careful stewardship. The more we control our own fingerprints, the clearer the story the rock itself can tell. Now let us unfold these methods into a small imagined study. A slow international mission to 3. I/ATLAS is approved. A trio of microprobes flutters near the object, each with distinct roles. One conducts high-resolution imaging and maps the surface texture, revealing a patch of unusual specular reflection. The second deploys a gentle radar probe, locating a subsurface cavity. The third samples surface dust with a tiny scoop, returning minute quantities to a sealed analysis chamber where spectrometers and isotopic analyzers patiently pass composition. Over the course of weeks, the team records anomalies, an unexpected alloy, a non-terrestrial isotopic skew, and a microscopically regular etched band. The data does not shout, it whispers, but the whisper is persistent and coherent. Scientists confer, protocols are verified, contamination sources are ruled out, and a global community leans in with careful excitement. Encoding methods are another calm frontier. If a civilization intended to leave messages, What durable media might they choose? Dense crystalline structures can store information through dopant patterns. Layered mineral laminates can hold sequences of micro-inclusions with varying optical properties. Etched patterns at nanoscales can be resilient to erosion. The principle of durability suggests any deliberate encoding would favour simple, robust formats. Repeating geometric patterns, prime number sequences, or mathematically universal constructs that a rational observer could recognise. Detecting such intentional patterns amid natural noise is like hearing a simple melody within the wind. Interpretation requires patience and cross-disciplinary humility. Geologists, chemists, planetary scientists, materials engineers, and linguists would all examine the evidence. Each discipline brings its own questions and biases. The goal is to converge on narratives that are consistent across methods. Science, in this context, is a social process. A global chorus of experts, slowly building confidence through replication and careful elimination of alternative explanations. Finally, consider the emotional texture of such a discovery. Finding a clear, repeatable anomaly on an interstellar rock would not be a cinematic explosion of certainty. It would be a series of calm confirmations, incremental and cumulative, the way a long mystery is solved by patient accumulation of facts. That slow unveiling is part of the wonder. It respects the universe's scale and our own capacity for measured discovery. Before we close this chapter, a gentle retention spark. In the chapters ahead, we will examine how we might prepare Earthside laboratories to analyse returned grains, how to design missions that minimise contamination, and how to craft public communication strategies for discoveries that unfold over months or years. These are human-scale practices that shape how we receive cosmic stories. As you rest, visualise a microscope stage bathed in soft light, a tiny particle from a distant path resting under a lens, and a team of quiet scientists tracing its features. The whole cosmos compresses into that small, careful act of reading. Chapter 12. If we did summon it, motives, intentions, and why anyone would send a visitor. As we drift further into this gentle investigation, let us imagine for a moment that the passing visitor, the interstellar pebble, the silent rock, the possible carrier, was not entirely accidental. What might motivate a distant mind to send something our way? What intentions could underlie such slow, patient outreach? Tonight we will explore motives in plain, calm language, separating practical reasons from philosophical ones, and keeping curiosity rooted in scientific humility. First, begin with the quietest motive of all, knowledge. Curiosity is not unique to humans in our imagination. It is a simple, persistent logic. A distant civilization, or an automated archivist built by that civilization, could be motivated by a desire to understand, to sample different stellar neighborhoods, to compare chemistry across many worlds, and to build a catalogue of planetary stories. Sending tiny scouts, low-cost, long-lived probes, is an efficient way to gather distributed data. Imagine a global weather network on Earth. Many small stations spread across vast regions produce a far better picture than a single massive device. In cosmic terms, a distributed fleet of pebble probes offers breadth and redundancy. Their arrival would be an act of scientific quietude, a methodical attempt to learn about us without interference. A related practical motive is resource reconnaissance. The galaxy is not uniform. Some systems are richer in certain minerals or isotopes than others. A civilization planning for very long-term survival might dispatch scouts to survey resource availability across nearby star systems. These missions need not be aggressive. They are scouting missions in the anthropological sense, catalogues and maps, rather than invasion plans. The probes would be small and unobtrusive, designed to mark deposits and report back so that future, well-considered projects might make use of those data. This kind of motive is pragmatic and far-sighted, reminding us that long-range planning often looks like careful bookkeeping. Preservation and archival intent is another gentle reason to send objects. A civilization concerned about cosmic threats, supernovae, gamma-ray bursts, or local catastrophes might want to distribute copies of its knowledge, culture, or genetic archives across safe harbours in the galaxy. Hitchhiking a durable archive inside a rock is an elegant strategy. Nature provides shielding, and the rock's inertia carries the archive onward for eons. If such motives exist, a visitor like 3i/ATLAS could be a seed bank, a library fragment, a little corner of another culture preserved in mineral form. The aim is not contact, it is continuity. We should also contemplate the idea of cataloguing intelligence. Civilizations might be motivated to map where interesting processes occur, chemical anomalies, seasonal biomarker fluctuations, or energy patterns inconsistent with natural processes. Sending scouts is a low-cost way to confirm remote observations. If a bright beam transmission, a detected techno-signature, or an unusual infrared excess appears in a catalogue, a careful analyst might dispatch a slow probe to verify. It's the cosmic equivalent of sending a researcher to a remote field site to check an instrument reading. Precise, patient, and non-confrontational. There are quieter, more philosophical motives as well. A civilization might be motivated by curiosity mixed with reverence, a desire to witness diversity in the cosmos, and to honour it by careful observation. Their probes could operate under a code of non-interference. Catalogue, observe, and record without contamination. Such an ethos mirrors the ethical frameworks we discussed earlier about how to approach less advanced worlds. If a visitor arrived with that intention, their presence would be archival rather than interventionist. Not all motives are benign by intent, but many are benign by design. Consider the practicalities of risk. Sending large, energetic expeditionary forces across light years is enormously expensive and risky. The cost-benefit calculus for distant civilizations often favours small scouts and archives over grand invasions. Even a civilization capable of galaxy-spanning capabilities might prefer subtle reconnaissance first, allowing time for ethical discourse and careful planning before any intrusive action. In other words, the first arrival is likely to be quiet and cautious. Now let us touch calmly on the darker possibilities, not to alarm but to acknowledge completeness. Motives could include surveillance for perceived threats, preemptive resource claims, or strategic positioning. These scenarios are often foregrounded in speculative fiction because they raise drama, but the practical realities make them less likely as immediate explanations. Large-scale, aggressive strategies require sustained energy, coordination, and long-term risk tolerance. They are not efficient for initial contact. If we imagine distant actors thinking in patient, multi-generational terms, as any civilization capable of interstellar messaging likely must, prudence and measured reconnaissance remain the likeliest first steps. How might we test intent if we found evidence of an implanted device or an archival payload? There are a few thoughtful scientific approaches. Content analysis with restraint. Carefully read any discovered archive for content that is clearly informational versus content that manipulates or commands. An archival fragment would likely prioritize physics, mathematics, and geography, universal languages, rather than directives. Behavioral observation. If a probe activates, observe whether it attempts communication, remains passive, or alters its host environment. A passive recording probe suggests archival intent. active efforts to influence would require deeper ethical debate. Pattern recognition. Look for signatures of deliberate non-interference, lock and key encoding formats, safety protocols, or time-locked releases that suggest respect for the autonomy of the target system. Distributed consultation. Involve broad, diverse international scientific and ethical bodies before acting. Testing intent requires collective wisdom rather than hasty, unilateral response. There's also a hopeful nuance. Intent and capability are not the same. A find that appears engineered does not automatically imply agency with malevolent goals. More often, practical considerations, energy, patience, and economy lead to benign or neutral strategies focused on learning and preservation rather than dominance. That observation can soothe the imagination. Even if a visitor is deliberate, its arrival could be as gentle as a library book placed on our doorstep. To close this chapter with a quiet image, imagine a slow, ancient conservatory of knowledge in some distant system where elders decide to send small, durable seeds of culture into space, not to conquer, but to remember. Each seed is embedded lovingly into a pebble and set adrift, a way to say, we existed, we learned, and we hoped some patient mind might one day find our notes. If such intentions exist out there, their first visitors will approach like librarians rather than conquerors. In the chapters ahead, we'll explore how we would decode such archives, how to responsibly curate any recovered materials, and how to communicate findings to a world that may react in many ways. For now, let the idea of patient motives, curiosity, preservation, and careful reconnaissance rest in your mind like a quiet lantern illuminating a small page in an immense book. Chapter 13. The subtle language of motion. How we might recognize a deliberate trajectory. Tonight, we turn our attention to the slow, patient geometry of movement, the paths traced by interstellar objects as they traverse the void. Motion, like words on a page, can carry meaning, or, at the very least, hints. If a visitor arrives not by accident, could its trajectory itself tell a story? Could a careful observer detect signs that an object's path was nudged, calculated, or chosen to reach our system intentionally? Begin with the concept of hyperbolic orbits. Most interstellar objects pass through our solar system in hyperbolic trajectories, arcs that do not close, meaning the object will eventually leave again. The precise angle and speed at which it enters, its inclination relative to the ecliptic plane, and its perihelion distance all form a delicate signature of its history. Small deviations from randomness could indicate prior influences, like gravitational nudges or even artificial guidance. In other words, its orbit is a letter written in the language of motion. We must also consider statistical expectation. If we examine thousands of objects passing near the Sun, most will follow patterns determined by the galactic tide, nearby stars, and local cloud density. An object that consistently appears on unusually precise paths, especially paths that intersect regions with life-supporting planets, would stand out in the cosmic noise. Its trajectory might be interpreted as intentional, not because it shouts, but because it quietly violates the norms of natural probability. Gravitational sweet spots are another subtle cue. Interstellar objects sometimes pass through zones where the gravitational influences of multiple bodies combine in delicate balance, such as near Lagrange points or resonances with major planets. If a body seems to have purposefully entered such a zone, lingering longer than expected or taking a path that maximizes observation potential, it may suggest intelligent planning. These are gentle fingerprints, like the faint brush strokes of a careful painter. Time is also a critical factor. Unlike short-lived spacecraft launched for immediate exploration, interstellar visitors operate on cosmically slow scales. An object arriving at a predictable point centuries or millennia after a signal could indicate patient foresight. Its timing signature would be as important as its spatial path. Even a millimetre per second deviation in initial velocity can translate to a light-year difference over centuries. So achieving a deliberate encounter requires extraordinary precision and patience. Next, consider how rotation and orientation contribute to the story. Many interstellar objects rotate as they travel. Their spin axis, angular momentum, and reflective surfaces can reveal past interactions. For example, a spin rate unusually stable over centuries, or a reflective orientation that maximizes visibility at perihelion could suggest design. It is not a blaring announcement, but a quiet, subtle feature embedded in physical behavior. We can also study environmental interaction. Outgassing, dust emission, and surface erosion are natural processes that can slowly alter an object's trajectory. By modelling these effects precisely, scientists can backtrack an object's path and detect whether deviations align with natural forces or subtle external nudges. A trajectory that corrects itself against natural perturbations could hint at a controlled adjustment, a gentle, guiding hand across light years. Imagine a small, patient narrative, a probe released from a distant star system millions of years ago, intended to observe emerging life in neighbouring systems. It drifts quietly, relying on gravitational nudges from minor stars, subtle radiation pressure, and occasional gas clouds to maintain course. Every century, its tiny thrusters activate to correct minute deviations. Finally, it enters our solar system along a path carefully calculated to maximize observation while avoiding collision. Its arrival is neither dramatic nor sudden. It is a whisper of motion across space, a slow and deliberate dance that requires no immediate notice but carries intention in its geometry. Finally, reflect on what this teaches us about interpretation. Recognizing a deliberate trajectory requires patience, statistical awareness, and careful modelling. It is not a matter of certainty at first glance, but a gradual accumulation of clues. Scientists build simulations, track deviations over time, and compare observations with millions of expected natural paths. Only when anomalies consistently resist natural explanation do they attract focused attention. As you rest into this vision, imagine the solar system as a quiet stage, with countless objects tracing arcs through invisible grids of gravity. Some move purely by chance, others by natural forces, but among them, one may trace a path that hints at foresight, care, and deliberate observation. The cosmos speaks in the language of motion, subtle, patient, and waiting for someone with time and attention to notice. Chapter 14. The Whisper of Energy. Detecting subtle signatures of a hidden probe. Tonight, we turn our attention to whispers that are barely there, the faintest traces of energy that could reveal the presence of something intentionally embedded within an interstellar object. Even the quietest probe, designed for centuries of observation, cannot entirely hide from the laws of physics. By studying these subtle signatures, we gain the ability to detect what is otherwise invisible, without disturbing the visitor's delicate journey. Begin with thermal emissions. Every object with mass and internal activity radiates heat. In the cold reaches of space, a probe's minuscule warmth stands out against the nearly absolute zero background. Sensitive infrared instruments can measure deviations in temperature as small as fractions of a degree. Imagine a rock drifting silently, but a small pocket inside emits just enough energy to tip the thermal balance, like a candle flickering under snow. Observing that flicker over time allows scientists to isolate potential sources of activity. Electromagnetic anomalies provide another layer of information. Even dormant electronics have residual electromagnetic effects. Tiny currents in microcircuits, subtle magnetization, or minute dielectric differences can create signatures detectable by precision magnetometers and radio instruments. These effects are faint, whispers rather than shouts, but they carry the rhythm of hidden activity. With careful observation, scientists can separate natural magnetic variations from those that might indicate embedded technology. Consider also subtle light reflection. A probe's surface may reflect sunlight differently from the surrounding rock. Tiny facets or coatings can create predictable glints or polarization patterns that repeat with rotation. By modelling the rotation of the object and observing these patterns, scientists can detect something unusual without physical contact. It's akin to noticing a small, deliberate ripple in an otherwise calm pond, a quiet signal that something lies beneath the surface. Radio emissions, even unintentional, are another potential clue. Components that store or move electrical charge can occasionally discharge tiny bursts of radio frequency energy. While these bursts are weak, advanced listening arrays designed for deep space observation can identify and localize such anomalies. The trick is patience. Repeated monitoring over months or years, correlating changes with rotational periods or orbital position, gradually reveals persistent, non-random patterns. Internal structure can leave telltale signs as well. Variations in density, composition or elasticity affect how the object responds to external forces, including tidal stress from planetary flybys or micrometeorite impacts. Sophisticated radar and LiDAR studies can detect these anomalies. By modelling expected behaviour for natural rock, deviations become visible, like a violin string that vibrates slightly differently because a hidden weight has been added. We must also account for intentional camouflage. Any advanced civilization attempting to hide a probe would carefully engineer it to minimize detection. Low-power emissions, thermally insulated casings, and materials chosen to blend naturally with the host object. Detecting such a device requires not just instruments, but subtle reasoning, simulation, and patience. Scientists would need to observe over extended periods, comparing behavior with natural models, patiently teasing out irregularities. Now let us imagine a slow, hypothetical observation scenario. A small interstellar visitor enters our solar system. Observatories across Earth and in orbit carefully track its thermal signature, rotation, and magnetic field. After months of observation, a tiny repeating thermal anomaly is detected, just a fraction of a degree higher than expected. Rotation measurements reveal a pattern. Every 3 hours, a faint glint appears from a fixed patch. Radar scans reveal a subtle void within the otherwise homogeneous interior. Each clue alone might be dismissed, but together they form a coherent narrative. The patient observers recognize the possibility of an embedded device, and their careful, calm methodology prevents premature conclusions. These methods also teach us humility. The signals we detect are faint. Noise is inevitable. Cosmic rays, micrometeorite impacts, and thermal fluctuations all create background activity. Separating signal from noise requires repeated measurements, statistical modelling, and collaboration among multiple observatories. This is a slow process, an exercise in patience and observation rather than immediate discovery. Finally, consider the emotional texture of such detection. Unlike the sudden revelation of a cinematic encounter, the discovery unfolds over months or years, one quiet hint at a time. Each small confirmation is a gentle thrill, a deepening of our understanding, and a reminder of the scale and subtlety of the universe. The process itself becomes meditative, following the faint trail of energy, refining models, and gradually uncovering hidden presence. As you rest in your imagination, picture a distant rock drifting silently, nearly invisible against the black sky, yet speaking to us in whispers of heat, light, and subtle magnetic rhythm. Patience and careful observation allow us to listen, to read these signals, and to approach understanding without rush or alarm. Chapter 15. Approaching the Visitor. How we might safely study an interstellar object. Tonight we explore the delicate art of approach, not rushing, not startling, but patiently studying an interstellar visitor while preserving both its integrity and our own. A small probe, or even a naturally wandering rock with curious anomalies, presents a rare opportunity, a chance to learn from a distant corner of the galaxy. Yet approaching it requires patience, planning, and respect for the subtle physics and possible intelligence it may contain. Begin with distance. Observing from afar is our first, safest option. Telescopes, radar, and infrared instruments allow us to gather vast quantities of data without physically touching the object. Tracking rotation, thermal emission, surface reflection, and trajectory over months or years provides a calm, continuous stream of knowledge. Each measurement adds a layer to the story, building a complete picture before any closer interaction occurs. Patience here is the most important virtue. Next, consider flyby missions. These missions gently escort a spacecraft past the object without orbiting it, using minimal thrust to maintain a safe distance. By imaging the surface, analysing reflected light, and sampling near-object particles with dust collectors, we can gain rich information without imposing risk. Each pass is a measured conversation with the visitor, slow, deliberate, and non-intrusive. Orbital insertion, if deemed safe, is the next level of observation. A spacecraft carefully matches speed and trajectory with the object, entering a stable orbit around it. This allows detailed study of rotation, internal mass distribution, and long-term monitoring of surface changes. The orbit must be delicately chosen. Too close, and the object's own gravity or irregular rotation could endanger the spacecraft. Too far, and resolution diminishes. Precision is key, and small adjustments are made gradually. Sampling the surface or ejector comes next, if it is safe and appropriate. Gentle mechanisms like microlanders or robotic arms can collect grains without disturbing the whole body. Even tiny particles contain immense information. Mineralogy, isotopes, microfossils of cosmic dust, or potential embedded technology. The collection process is slow and deliberate. Each touch is measured, each movement carefully planned to preserve both scientific value and the visitor's natural state. Consider robotic internal scanning. Non-invasive techniques, such as ground-penetrating radar, X-ray tomography, and low-frequency vibrations, allow us to probe internal structure without breaching the surface. These methods can detect cavities, heterogeneities, or potential embedded devices. The principle is gentle patience, observation first, alteration only if necessary. We also must prepare for potential activity. If a probe inside the object is still operational, it may respond to our approach, intentionally or unintentionally. By maintaining safe distance, observing electromagnetic emissions, and avoiding sudden maneuvers, we minimize risk to both spacecraft and visitor. The goal is knowledge without interference, to let the visitor continue its journey while quietly collecting information. Communication strategy is another subtle concern. Data from the visitor must be transmitted safely back to Earth, without alerting or confusing the object if it is active. This requires careful bandwidth management, encryption, and timing. In essence, we speak in whispers, listening before attempting any louder signals. Finally, ethical frameworks guide the entire approach. Scientists consider the principle of cosmic respect. Avoid contamination, prevent unintentional disruption, and preserve the visitor as a record of distant processes. We learn not just to study, but to steward, observing as a caretaker rather than a conqueror. Patience, respect, and careful procedure are the hallmarks of this phase. Imagine a slow cinematic sequence. A small spacecraft glides gently toward a drifting rock, its instruments humming softly. Cameras capture minute surface changes, spectrometers analyze reflected light, and infrared sensors detect faint heat emissions. Over months, the spacecraft orbits, documenting every detail without touching, preserving the visitor as it drifts silently through space. Each observation is a note in a symphony of discovery, calm, deliberate, and rich with meaning. As you relax into this vision, feel the patience required to truly understand the cosmos, the quiet, steady work of observing, listening, and slowly piecing together a story written across light years. The process itself becomes meditative, a careful dialogue with the universe. Chapter 16. Listening for a message. Interpreting subtle signals from the visitor. Tonight we turn our attention to the quiet possibility that a visitor may carry a message, not shouted across space, but whispered in subtle patterns, waiting for patient observers to notice. If an interstellar object like 3I/ATLAS harbours an intentional probe, it may transmit information using signals that are barely perceptible, faint radio emissions, optical flashes, or encoded electromagnetic patterns. Understanding these signals requires calm observation, careful analysis, and a willingness to listen without expectation. Begin with the nature of faint transmissions. A probe travelling across light years may only emit tiny bursts of energy to conserve power. These pulses could be irregular, very brief, or hidden within the natural electromagnetic noise of space. Detecting them demands sensitive instruments and extended monitoring. It is not a moment of sudden revelation, but a slow, patient accumulation of evidence. A rhythm of faint signals gradually revealing themselves to those who are attentive. Consider modulation and encoding. Even the simplest message can be disguised within variations of frequency, amplitude, or polarization. Patterns may be mathematical, sequences of prime numbers, Fibonacci numbers, or repeated geometric arrangements. Others may encode chemical or physical data, spectra, ratios, or structures meant to convey universal truths rather than language as we know it. Decoding such patterns requires not only technology, but imagination. The ability to recognize intentional structure in subtle variation. Timing is another delicate clue. A message may synchronize with rotation, orbit, or external celestial events to remain detectable to a patient observer. For instance, a probe may only emit a burst when sunlight falls at a certain angle, or when passing near a specific gravitational point. Observers must track time carefully, noting correlations over days, months, or even years. The narrative unfolds gradually, a quiet dance of signal and observation. Noise filtering is crucial. Cosmic background radiation, solar flares, and micrometeorite interactions all produce signals that can mask deliberate messages. Sophisticated statistical models and repeated observation help separate natural fluctuations from potential communication. Each confirmation is small and deliberate, like hearing a single note in a vast symphony, but over time these notes may form a melody, or a coherent message. Consider the possibility of multi-layered signals. A probe may transmit different types of information through separate channels simultaneously. One channel for positional data, another for environmental readings, and another for encoded cultural information. Observers would need to correlate these layers carefully, ensuring they do not misinterpret one as noise or misread their relationships. Patience, precision, and an open mind are essential. Now imagine a slow, deliberate observational campaign. Radio telescopes around the globe monitor an interstellar visitor for months. Patterns emerge, subtle pulses repeating every few hours, slight variations in wavelength, and faint optical glints aligned with rotation. Analysts compare results across multiple instruments and time zones, filtering out natural interference and human-made noise. Slowly, a coherent sequence begins to appear, suggesting that the signals are not random. Each observation is a step in a long, methodical decoding process. Interpretation requires humility. Even if a signal appears intentional, its meaning may not be immediately obvious. Some patterns may be universal, mathematics, physics, or chemical structures. Others may encode knowledge specific to the sender's system. Patience, cross-disciplinary analysis, and international collaboration are crucial to avoid hasty conclusions. The discovery is a process, not a sudden event, a gentle unfolding of cosmic information over time. Finally, consider the emotional texture of such a discovery. Unlike dramatic science fiction, the thrill lies in the slow accumulation of understanding, the careful recognition of patterns, the confirmation of anomalies, and the gradual unveiling of information across months or years. This process teaches a kind of meditative attentiveness, a deep appreciation for the patience required to truly engage with the universe. As you relax into this vision, imagine sitting in a quiet observatory, watching a distant rock drift silently through space, listening with sensitive instruments, and slowly hearing the faint rhythm of a message encoded across light years. Each pulse, each glint, is a gentle invitation to understand, and the process itself is as calming as it is fascinating. Chapter 17. Tracing the Journey, Reconstructing the Visitor's Path Through Space. As we follow the faint signals and subtle motions of an interstellar object, our attention turns to understanding where it came from and how it reached us. Every movement, every emission, and every subtle interaction with stars and interstellar clouds carries information about its long journey. By carefully reconstructing its path, we begin to read the cosmic story etched in its trajectory. The first step is precise orbit determination. Using repeated observations from multiple telescopes, scientists can measure the object's position, velocity, and acceleration with extraordinary accuracy. These data allow researchers to calculate the object's incoming trajectory, estimate its velocity relative to the Sun, and identify how it might have been deflected by gravitational influences over millions of years. Even a tiny deviation in speed or angle can reveal past encounters with other stars, molecular clouds, or unknown phenomena in the interstellar medium. Spectral data add another layer of information. By analyzing the light reflected from the object, scientists can determine its chemical composition, surface structure, and isotopic ratios. Each element and mineral hints at its place of origin. A high concentration of certain isotopes may indicate formation near a particular type of star, while unusual mineral patterns may point to regions of the galaxy with specific cosmic histories. Combining trajectory data with spectral signatures creates a multi-dimensional map of the object's life before it entered our solar system. Gravitational modelling helps fill in the gaps, Over millions of years, objects travelling between stars are nudged by passing stars, the galactic tide, and dense molecular clouds. By simulating these interactions, researchers can estimate how the visitor's path was influenced over time. This careful reconstruction is like piecing together a delicate puzzle, where each missing piece can subtly alter the picture. Cosmic dust and micrometeorite accumulation also tell a story. Tiny impacts slowly coat an object, leaving a record of its travels through interstellar space. By analysing surface grains, scientists can estimate how long the object has been in transit, the density of the medium it passed through, and the frequency of collisions. These microhistories add texture and depth to the broader narrative of its journey. In combination, these methods allow us to imagine the object's voyage. Perhaps it was once part of a planetary system, ejected by gravitational interactions with a massive planet. Maybe it drifted for millions of years through interstellar clouds, its surface slowly sculpted by cosmic dust and radiation. Each piece of data adds a chapter to the story, transforming an anonymous rock into a messenger of distant worlds. Finally, understanding the journey is also an exercise in perspective. The vast distances and timescales involved remind us of the patience inherent in the cosmos. The object that has reached our attention did so not suddenly, but as the result of eons of motion, a silent traveller shaped by countless subtle forces. This realization deepens both our scientific curiosity and our sense of wonder, grounding the mysteries of 3I/ATLAS in the beautiful logic of physics and cosmic history. Chapter 18: Chemical Clues Unlocking the Visitor's Origins. As we continue to follow the visitor's subtle signals and reconstructed trajectory, we now turn our attention inward to the very substance of the object itself. Its chemical composition, isotopic ratios, and microstructural features serve as a cosmic archive, silently recording the conditions of its birth, the environments it passed through, and the processes that shaped it over millions of years. By reading these chemical clues, we begin to uncover the story of where it came from and the universe it travelled through. Start with the elements themselves. An interstellar rock carries a mixture of silicates, metals, and perhaps ices, each telling a different story. Silicate minerals often form in high-temperature environments, hinting at formation near a young star, where stellar heat and radiation sculpted dust into crystalline structures. Metals like nickel and iron can point to processes involving planetary differentiation or ancient collisions within its home system. Even trace elements, present in parts per million, act as fingerprints of astrophysical history. Detecting unusual abundances such as isotopes not commonly found in the solar system can indicate formation around a star of different metallicity, or exposure to cosmic processes far from our own sun. Isotopic ratios carry another layer of narrative. Ratios of oxygen, carbon, or nitrogen isotopes are remarkably stable over time and are influenced by local stellar environments. By comparing these ratios to known cosmic baselines, scientists can hypothesize whether the rock originated near a massive star cluster in a calm interstellar cloud or near a system with a high supernova rate. Subtle variations in isotopes may even reveal exposure to cosmic radiation over millions of years, acting like a slow natural clock that traces its passage through the galaxy. Next, consider the surface chemistry. Cosmic rays, micrometeorites, and interstellar dust gradually alter the surface of an object. In some cases, these effects leave recognizable patterns. Tiny pits, layers of oxidation, or accumulation of rare cosmic grains that can be studied in detail. Observing these changes allows scientists to infer the density of the medium it travelled through, the duration of transit, and even interactions with magnetic fields in interstellar space. Each layer is like a page in a diary, recording subtle events that would otherwise go unnoticed. Organic compounds may also be present, though in minuscule quantities. These molecules, formed in distant interstellar clouds, could survive long journeys inside protective rock. Amino acids, complex hydrocarbons, or polycyclic aromatic compounds are rare but deeply informative. Their presence hints at the chemical richness of other star systems and provides insight into processes that may be universal prerequisites for life. Even without implying direct life, such compounds serve as cosmic markers, connecting distant chemistry to our own understanding of planetary formation. Imagine a careful analysis. A laboratory equipped with spectrometers, electron microscopes, and mass analyzers studies fragments of the visitor. Scientists trace subtle patterns. A spike in heavy oxygen, isotopes, suggest formation near a young massive star. Slight enrichment in certain metals points to ancient planetary collisions. Tiny inclusions of cosmic dust reveal passage through dense interstellar clouds. Each discovery is layered, building a multi-dimensional portrait of the object's origin. These chemical narratives are further enriched by simulation. By combining observed composition with astrophysical models, researchers can reconstruct possible formation scenarios. Perhaps the object was once part of a protoplanetary disk, orbiting a star hundreds of light years away. Gravitational interactions ejected it into interstellar space, where it drifted for millions of years, exposed to radiation, dust collisions, and occasional magnetic perturbations. Over time, it acquired the subtle isotopic and chemical signatures we detect today. What makes this exploration so mesmerizing is the intersection of patience, precision, and imagination. Unlike a sudden revelation, each clue requires careful measurement, comparison with known cosmic baselines, and the gradual assembly of a narrative that spans vast distances and unimaginable timescales. Observing, hypothesizing, and confirming. These are quiet, deliberate acts, like reading a story written across light years, sentence by sentence. Finally, the chemical story does more than satisfy curiosity. It connects us to the universe beyond our solar system, revealing that the materials of distant worlds can arrive at our doorstep. Each element, isotope and compound carries with it the imprint of cosmic history, whispering tales of stellar nurseries, interstellar drift, and the patient forces shaping matter across the galaxy.